Very welcome to the third colloquium in this semester, and it's pleasure to have Professor Andrzej Buras from Technical University of Munich today with us, and he'll be delivering a colloquium talk on Flavour expedition to the Zeptouniverse. And he didn't need much introduction because he's quite well known in his field, and outside field also many people know him. So only thing I would like to mention that he has contributed quite actively in the particle physics. So we all are thank you for him. Recently he got a Max Planck Award in 2020. So we also congratulate him for this achievement. And with further delay, I would like to hand over the forum to Professor Buras and invite him to deliver today's physics colloquium on Flavour expedition to the Zeptouniverse.
Thank you very much. As we have seen, the landing, virtual one, took some time, but I'm very happy I finally arrived in India. I have never been in India. And this is the first time, and this is also the first time I'm really giving a talk like this. And I would really like to thank Professor Nandi for all these nice comments and in connection to the award. And let me begin this talk with a few personal comments. Last year was a very interesting year for me and important one, not only because of this Max Planck Medal, which I received, as you will see during the talk. It was awarded to many well-known physicists much better than me, but in particular because this was 50 years after I started doing particle physics, and during these 50 years, there was a dramatic change in physics, but not only in physics, as you can see here. And you can also see that while I'm rather serious in 1970, I'm smiling in 2020. And there is the reason, because my generation was very privileged that we could witness very many discoveries in particle physics, which the younger people now cannot. And so let us look for a moment at the next transparency, showing what we know today. Don't worry, for those who are outside particle physics, this will be a very simple talk, I hope. And in 1970, what we knew as far as quarks are concerned is up quark, down quark, strange quark. And in fact, some people like the famous Heisenberg thought that these were only some mathematical objects which Gell-Mann introduced to explain some spectra. On the side of leptons, we knew only electron neutrino, muon neutrino, which is given here, electron and muon. Among the forces, really, we knew only photon. And since many years, of course, gluon was not even mentioned, I think, by Gell-Mann in 1970. And of course, there was already proposals for the standard model, but definitely Z was not yet discovered at the time, and W was not discovered. And eventually came Higgs, and all these other particles were discovered. 2012, Higgs was discovered, fantastic ceremony. And we know now from the study of the couplings of Higgs to the fermions that indeed Higgs pretty well describes the masses. We know also already for some time that Higgs has nothing to do with the proton and neutron mass. We know already through very complicated lattice calculations that this is related to the masses of proton neutron, and the masses of proton neutrons come from strong force. Now, this is what was last time, 2012, and one has to say there is some frustration of a community, in particular theorists and also experimentalists, of course, who worked already on many things. And this frustration is expressed in some talks, which are open like this one by Christoph Wetterich, who is an eminent theorist and a very good theorist, one of the best in Germany. But as you can see, we see Sahara. No supersymmetry, no technicolor. Technicolor was suggested in 1980 by Weinberg and Susskind as a new strong force. No additional Higgs particles, no low energy, high dimensional scale, like for instance, Randall-Sundrum scenario. Now, Christoph is really an eminent theorist. I know him already for many years. But what can I say? His vision is totally wrong. So let me go to another transparency and see what another eminent theorist, John Ellis, my collaborator from CERN, is telling us. Now, John, as well known, worked for many years on supersymmetry by us called SUSY. So he's waiting for SUSY already for 40 years. And he's a bit more optimistic. This is collider physics view. You can see there are some new physics summits out there. I added also one number here. The problem is John is getting old. In 2046, he will turn 100 in July, and I will turn 100 3 months later. And truth to tell, I cannot imagine that any SUSY out there is waiting for us. And this is even worse because the European strategy for high energy physics will definitely not allow us to see directly new physics particles with masses above 100 TeV. Maybe Large Hadron Collider we see still something, but it will be 5, 6. So if you really want to go much farther, like 200 TeV, which corresponds roughly to the Zeptouniverse I will be talking about, the only way to do is through quantum fluctuations. And we have classical analogies here. Like this French gentleman many years ago predicted the existence of Neptune by noticing anomalies from Kepler laws in the orbit of the Uranus. And he predicted, this is fantastic, he was a mathematician, he predicted the accuracy of 1 degree, which was confirmed by Gottfried Galle. There is an English gentleman who also claims he did it, but you have to publish things, and he didn't publish. So the other one got the credit. Black hole, Nobel Prize 2020 is another analogy. Of course, all dark matter searches that you really don't see the thing, but you can somewhat feel what is going on. And in fact, Enrico Fermi already in his 30 with his theory basically saw some footprints of W, Z a bit later. This was 73. And both were indirectly discovered much later. And now comes my vision. And I really hope that you will remember this transparency until your last days. And here it is. And this is the Flavour physics, as seen from my point of view. This is my son, Alan, who took this photo. Unfortunately, I was not there myself. Here in front, very boring. This is Basecamp, standard model. Then we have an energy gap, which is crossed using some theoretical methods, which I will not discuss maybe in the discussion, standard model effective theory. And then we have some crevices, so definitely a very dangerous route. Eventually, let us hope we come to new physics summits. So this is what we will be trying to do in this talk. And the point is, this is an expedition from Atto universe, 10 to minus 18 meters, and 10 to minus 21 meters. And this is a bit of a problem for particle physics, because it's extremely difficult to really imagine how small these distance scales are. Astrophysicists have a much easier time. They show photos like this, and one like you have announced my talk. And they can even show things like that there's some Kepler searching for new lives, the public is excited, and so on and so on. And therefore, in 2009, to advertise better particle physics, I got an idea of going to a dual picture of the short distance scales, which was very much liked by my colleagues in string theory, who work with duality between the coupling and inverse coupling, so weak versus strong. Now, couplings are usually in gauge series dimensional, in 4 dimension at least, and here, of course not, but let's forget it. And let's just take the minus psi away. And this is a dual picture I will show you now for a few minutes, and some interesting things are coming out of it. So let us train on something what you very well know, and this is the moon. In this picture, moon corresponds to nano universe, accidentally, and this is very good, roughly 10 to the 9th meter is the distance to the moon. And you can be really impressed now what the nano technology is doing for us. I mean, you can imagine we all are as tall as the distance from the Earth to the moon. And these guys in this world are working at 1 meter. And this is really impressive, so I should praise them. But still, I'm teasing my eminent colleague, Abstreiter, who nanotechnologists maybe that are there in the audience, that is simply nothing. I repeat, nothing compared to what particle physics is doing. So let's go here. So what we have here is now Zeptouniverse in this language. This is 105 light years. And there is some object called Beta Ceti in this constellation. It is 97 light years away. And now in 1929, let's assume, in the year when Einstein and Max Planck got the first medal, Max Planck medal. Max Planck medal gave to him, I should get also this idea, but not for today. And if the signal at that time was sent to us, it will arrive at the 80th birthday of mine or John Ellis. So this is already very impressive, but now we are coming to Zeptouniverse, and this is 100,000 light years. So this is the object which I could find. Factor 2 is maybe not so important. This is Large Magellanic Cloud. So now in this language, this is the Zeptouniverse. As you can see, very impressive there. And even more impressive is our Large Magellanic Cloud. And now you can ask the question. Somebody has sent many years ago, 170 years ago, a message to us, maybe for my birthday, but probably not. And what was at that time on the Earth? And here's the answer. This is what we have. And I doubt this collaboration. I think this guy here is a spokesman, expected that I will be citing them. But this photo is really very good for my talk. And the reason is that, as you will see in this talk, Flavour expedition to the universe is really a true mammoth project. It's very difficult, but we should really try. So we are going now back to short distance scales, and the first person who should be credited for the route to short distance scale is an amateur, not Atlas, not others, but this guy who in 1676, Leeuwenhoek, discovered bacteria. He was a guy who could construct, he was amateur, he constructed many microscopes. One day, after magnification of by 300, he saw some moving creatures, animalcula, what he thought, small animals. And he was actually not very nice, but he was smart. He never told people how he built these microscopes. So he died, and nobody could still, until this Italian expert came, but as you can see from the age here, he came a bit later, started really looking further, and the other guys. But this had one advantage. There is no question about, no discussion like with Uranus and so on. The full credit is given to Antony van Leeuwenhoek for the first person who saw something which you cannot see in the naked eyes. I want to say here a few things about Robert Koch, maybe only mention. He's a very popular person these days, at least in Germany. And starting already many years and continuing until I would turn John Ellis 100, but I'm sure even longer, people really made a very big progress, in particular in the last century. And exploring, we are talking about it, nano universe and femto-universe, relevant for nuclear physics, low-energy experiments, particle physics, Zeptouniverse, which in fact was already explored for roughly like 10 years and so on. And now we are moving a bit farther. I mean, like 5 to 10 to minus 20 meters. This is through direct searches for particles at Large Hadron Collider you can get, but not more. So if you really want to go and explore whether there is anything like 50 TeV, 100 TeV, or maybe even more, you really have to do through quantum fluctuations, and these are rare processes, not only flavor violating, I will be talking about the other one, and this is this Zeptouniverse, which is our goal for today. And this is the base camp. I got an ERC grant. Actually, I started already early looking in these directions, and this is why I'm sitting here. My group is behind here, also now very small, as you will see in a moment. And looking at the Bavarian Alps, and it's really fun. I'm sitting here. I'm really sitting here now, and you can see some ladies behind me, but they're all dead, so there's no problem. They will not disturb us. And let's now move. This is maybe the moment. This is the first time I'm giving a talk in India. Let me introduce some collaborators, which of course played some role in getting Max Planck Medal and maybe others. And I started in 1988, 2005, and then continued high order calculation, strong interaction, 2-week decay corrections, flavor physics in the standard model, which I'm still continuing. And what I'm very proud, I had, as you can see, many students and many postdocs. We could analyze together 20 new physics models. I don't think there's any group in the world who could do it, but as you will see in a moment, I really want to spend a few minutes to praise them. I had fantastic people, and some of them you will see. At the moment, I have only one postdoc, and I will indicate it by a star. You will see later in a few minutes. And of course, I got support, otherwise I could not have this group. So these are my PhD students now, who of course now are, okay, these are some younger photos, older photos, who stayed in research. There are professors here and there. 3 of them succeeded, this Puchala, Heisch, and Weiler, to get a job in Munich, so we are still in contact, some other not. I have 2 wonderful ladies here who really very, Monica Blanke and Stefania Gori, who made already career. Unfortunately, some of them, and few of them very good ones, like Markus Lautenbach, Münz, and recently David Straub, left the physics. So this is not really good, but no, it's really bad, but this is what happens in our field. But let me thank still a few other people who I was involved. I got my PhD at Niels Bohr Institute. These were my first collaborators. John Ellis, whom you saw already, was my collaborator with Mary Kay Gaillard on Grand unification. The older generation maybe remembers some papers by Carl Gemmes and Myron Parton distributions. And already at the Max Planck Institute, I had these collaborators, in particular Bardeen and Gerard. They will appear still on the list soon. And I have to mention here my times at Fermilab. This is in connection with the so-called MS-bar scheme. This was the first correct matching of the full to effective theory. And we are sitting here, I think it was birthday of Bardeen. Now, I had many more collaborators. You have seen some of them, like Björken and a few others, and this was fun to work with them, many nationalities. The country which was really favored by me were Italians. You have seen all these Italians here. These are all Italians. I worked like Gino Isidori Silvestrini, and now you see the star. This is the only postdoc I have now. I retired, my ERC grant is to the end, and this is the next guy. You could definitely hire him. Now, Jason Abischer is another very good, and he didn't get the star, but he's equally good. And if I one day give a talk in Switzerland, I will put the star here. But now comes the most important transparency in this period. This is something which I doubt any theorist around the globe can show this one, and this is this one. So here again, we have Italian contingent, my daughter in physics, and 2 collaborators. But on this transparency, I really want to stress 2 young ladies, my daughter, Monica Blanke, and my granddaughter, the daughter in physics. This is physics, not really. My granddaughters are a bit younger, Jennifer Gierbach, and they will still appear in this talk. And these were really some of my best collaborators. So I had, as you can many collaborators, 123. This is not like Atlas collaboration. Really, I worked dominantly on the average only use to people, 16 countries, and so on. And this was really fun because there are different styles really in any country. People are educated in many ways. But to summarize, maybe the achievements of my collaborators working with me, these are the ones, the three I already mentioned. We were most productive. This is the number of papers we wrote together. And in fact, in these three cases separately, we never worked together and so on. And these are the ones were for citations. And at the end of this part, I will move to physics. I would like to thank three gentlemen who are unfortunately not among us anymore, but who really helped me a lot over the years and in a sense are helping me. And these are the three. I'm playing classical music all the time. And this is a part of some successes I had in physics. And for those who still do calculation by hand, and I would advise you to do it because then you see really what happens. If you have a difficulty, play triple concerto C major opus 56, you will solve all problems. This is try and write me an email that you really help. So the overture is now finished, and as may be expected by some, we are now moving to a symphony. And of course, it's Indian symphony. It has 4 movements. I will introduce further standard model. This is mainly for, maybe there are some people outside particle physics, I was told, so I will be very simple. There will be basically no equation in the talk anyway. Then I will present the technology, how really to reach with quantum corrections or virtualities, Zeptouniverse. I will discuss, of course, anomalies in Flavour data, and eventually I will be very optimistic, as you can see. Now, the reason I'm showing Beethoven is that my symphony cannot compete with his. In 1820, he composed the nines, but my symphony will be much shorter. So this is some advantage maybe sometimes. So let's begin with the first movement. And here we have 2 pillars, you know them, and 2 equations. And these are the only equations basically I will have in this talk. Well, I can tell you everything without equations. So the first equation here on the left is of course known. We are more interested in this equation because this gentleman told us that in order to really probe very low distance scales, we need high energies, high momenta, and so on and so on. And you should realize that we are completely, if you look here, in a completely different world. You are also in the first transparency you have seen. These are very short distance scale, completely different energies, and really time intervals which are far better than any laser today can do. Everything is based on relativistic quantum field theory with local gauge symmetries. There are many known names, but I mentioned only these 2. And the frontiers, from my point of view, frontiers of elementary particles is really search for physics laws at very short distance scales, which maybe will explain many things from us. So we have this Heisenberg principle, which tells us that to test Atto universe, we need some energies of the order of the top quark mass, 200 GeV. LHC will maybe give us, although the energy is much bigger, but this is proton-proton collisions, and so maybe we can test something like 4 TeV, maybe 5 TeV, but these are the scales which I here listed. And I doubt we can do better before 2046. And I should stress that really, if you want to see some particles of field, some footprints of 50 TeV particles, you have to wait to the next century if particle physics will survive. So really, if you want to go to 200 TeV, which roughly corresponds to Zeptouniverse central, you have to really go this way. And these are really the frontiers, very short distance scale, but as you will see, you need a very high precision. So let me now come back to this first transparency, but in a different view. We have this elementary particles, this roughly a periodic table, which has 4 families: neutrino family, electron family, up quark family, down quark family. And the scholars, these are different quantum numbers related to strong interactions. They have some funny charges, but we know these charges are what they are. And here are the flavors. We can also talk about flavors here. And we have 3 generations. And one point, which I will not go to details, but a fermion, these are all fermions, have usually 2 hands, left and right, as one knows from Dirac. And most of the interaction, these 2 hands are involved, but in the weak interaction on the left. And the point is that if you look at all these particles of these quarks or leptons in one family, and we have 3 generations, if you forget their masses, you cannot distinguish them. And it is already shown, because this is already properties, and this was, I think, shown first really after Higgs has been discovered by Uli Nierste, one of my PhD students, that you cannot have the 4th generation. The 4th generation, which would really act to weak interaction with the left hand. But you can have others, so-called vector-like quarks or maybe leptons, which work with both hands simultaneously in symmetry. So this goes. And now the only way I can distinguish particles in a given family is by the mass, which is increasing. But amazing thing is there are fantastic hierarchies here. And this is a Flavour puzzle, which theories of course want to explain, and there are many theories trying to say that this is not an accident, there is some symmetry which is broken, and this is the result. It's very difficult, but there are, of course, attempts. This physics is based on Feynman diagrams, which are also known in solid-state physics. He was a great man. And so let us look only at one. I have a big quark here, and it is changed to a charm quark. This is possible exactly with this W. And at the end, I have this neutrino, muon, and so on. And I have other properties. And the point is that what Feynman, as opposed to Schwinger, who had very complicated formulas, very mathematical, you simply have some Feynman rules for this vertex, for these interactions with a coupling. You have propagator for here going like the W. And you can draw more complicated diagrams. And the goal is you have to calculate probabilities, and they have to be measured, that you have to compare. And the second movement, I will tell you how it is going, but let me still continue and say a few things about the standard model. This is one formula which I really wanted to flash, not that some people are thinking we are only drawing diagrams. And here we have few things which are still open. This is based on this symmetry, which is spontaneously broken, but this is the phi is the Higgs or Higgs doublet. And this is at the level and the Landau-Ginzburg theory in the phase transitions in the solid-state physics. And there is another issue, so the Yukawa couplings related to the masses, which I was just discussing. So these are clearly open questions. But now I want to say that the situation with W's, which I said with this interaction, is a bit more complicated. And in fact, this vertex is not just a coupling. This is a full matrix here, which tells you that the strength of the interactions, as you will see in a moment, is different, dependently whether you stay in one generation, U to D, like this element, or this generation, C2S, and so on, or you really change across the generations. And so you can see this is already measured. These elements are measured to rather high precision in the last decades. And this is very hierarchical. Actually, it's basically unity, so nothing maybe exciting happens. And here it is small. And one thing which is interesting, that this is a unitary matrix. It has phases, and these phases are not small. They were measured, and these are related to the violation of so-called CP symmetry, charge, conjugation, and parity. And this is violated, we know, since many years. And we know also from Andrei Sakharov that we need this violation of the symmetry to explain our existence. These phases maybe would do it, but the point is that these coefficients here are very small, so we cannot. And another thing, to go further, and I will be talking about that processes, for those who are outside particle physics, just look at this transition like some chemical transitions where some object is going to another one, and this transition is governed by something which I cannot see, And this is, if there will be, I will explain soon. This is simply some kind of footprint of something that's going on. And now you can see there are some diagrams which are a bit more complicated. These are also called box diagrams. But now you have here some other diagrams where involve, for instance, Z, which cannot transfer the flare alone. It needs some diagram more complicated. But you could wonder, this was a name given by John Ellis to the diagrams, why penguin diagrams is like this. It doesn't look like penguin. But we have to realize that the Feynman diagrams do not look like Feynman either. So really there is no problem. The problem is only that my last statement is not quite correct, because there are really some similarities. Now, the standard model of strong interactions works very well, the spontaneously broken theory, and describes beyond gravity, how to accept gravity very well, but there are various questions which you cannot answer in this model. I mean, clearly there could be some elementary particles, forces. There is an issue why there is such hierarchy of interactions. Also, we've seen the CKM matrix, the Kobayashi-Maskawa matrix, and the masses. Why, for instance, neutron is heavier than the proton? If it was opposite, this talk would not take place, and we would never meet. Very bad. Now, why is our universe dominated by matter? And this is what I already said. In Big Bang, we had this CPR symmetry, but now we know there is not, and we need this Bragg, but at a much bigger level, dark matter, and there are many lists which I could list. I mean, many issues which I could list. None of these questions can be answered within the standard model. And we know that new physics must exist because somehow it has to be explained. Already dark matter we know is there, and of course neutrino masses which are not in the standard model, which I didn't mention. So it is really our duty to find it, if not through LHC, then through high precision experiments. And this is core flavor physics. There are some suppressed transition like lepton flavor violation, which has not been seen until today, or electric dipole moments, which have not been measured, and also like G-2 of muon electron. This is the anomalous magnetic moment of the muon electron. And so the basic question is now, for the rest of the talk, can quark flavor physics give us some insight in the dynamics at very short distance scale if no real signal will be found at an LHC, and we will know it in a few years? Is there a particle with 6 TeV, 5 TeV? If it's there, fantastic. So we can really play with two games, collider and flavor physics. Can we reach this high scale, so Zeptouniverse, by means of quark flavor physics? I will discuss, but because you can do it easier these days, and even maybe higher scales. So I'm now moving to the second movement. And this is a technology. This is probably the most important and the third movement, and there will be a very short one, second movement. And these are the main players which we have at the moment. These are the mesons, the bound states of quarks and anti-quarks, here listed. These are bound states, and they have some names. They are relatively light, and they can be produced in millions, in milliards in the collider, in high energy collision, and then they decay. This is not a classical decay. This is simply a transition, like I was showing you. Some kaon goes to pion, neutrinos, and so on and so on. So that what we say decay to lighter particles. And what is measured is the probability that these transitions, this decay occurs. We call it branching ratios. But I will use the name probabilities, and theories can calculate the probabilities, and you can start comparing whether the theory and experiment agree. So here, elementary kindergarten example, I have here as this B plus meson. There's some very complicated interactions through strong interactions. And now there is this transition through a W, and I end up here with 2 leptons. So I can calculate this probability. Feynman rules tells me what I have to do. I have 2 couplings, so this will be amplitude, will be GW squared. I have now a propagator, this 1 over mw squared, so I put it here, and there will be maybe some still parameters. Of course, any theory has still parameters, so I calculate this probability in the standard model. But now it happens that maybe there is some particle which we have never seen because it's very heavy, maybe 100 TeV and so on, and it also contributes. Not only millisecond, 10 to minus 25 second, comes and it changes the probability. So this is of some heavy particle, not necessarily some charge Higgs. So we know the rules. I calculate again this diagram, I add it, because this is quantum mechanics or quantum field theory, so there could be some interferences. I take module square in both cases to calculate probability. I go to experiment. The experiment measures a difference between maybe, whatever they see. They don't know whether there is a charge particle here. And if there is a difference, we know there must be something else there. The standard model is not the whole story, and there is some contribution. And then let me now go to a very specific example. And this is transition from this meson BSAP-S to 2 muons. I just choose it because I want to probe. Maybe there is something interesting there. In this blob, I have quantum fluctuation at very short distance scales. I don't see it. And the probability for these things to occur depends, of course, on the dynamics, which is hidden at very short distance scales, some particles, some diagrams, which I said. And the first thing I can do, I can calculate what is the probability in the standard model. And this was done by Gerhard Buchala and myself many years ago, when this was part of his PhD. And I show you one diagram. You immediately see that probability will be small because I have to have a number of weak couplings. There is also a top quark. We calculated really QCD corrections, really to reduce certain uncertainties. And one of the main achievements here was to notice that all the literature before us was wrong. We corrected by factor 2, which soon will play some role. So the question is, what is the probability for this decay? You can think about it for a moment. This is the result, 10 to minus 9. And the big error here, which we had in 93, because top was not discovered, we knew already it's above 100 TeV, but it was a bit bigger, so it was a big error. And this is amazing if you think for a moment. You go to Large Hadron Collider, this is maybe all transparency ATV, but even better is now. You produce 1 milliard of BSAP-S meson, and out of them, 3 on the average decay into 2 muons. And this calculation after top was discovered, was improved by me, by other people, also Jennifer took part, and there eventually some strong guys came and even improved. And now, of course, if the probabilities are small, theory said, okay, come on, there must be something. We will see something much earlier. Supersymmetry, 10, 100 among 1 milliard will be seen in BSAP-S. Then the people got a bit more modest. 2011, we constructed some minimal theory of fermion masses, probably my last attempt. It was not so successful. And in 2013, January, we produced also a paper based on this, predicting this probability. So not 3, but 5. Some people had 10. And then I was in Stockholm, unfortunately in July and not in December, at the EPS Stockholm conference. And this was 20 years later. This decay has been measured. So I thought 5, 7, 3. I was totally shocked, disappointed. This was the probability, fantastic agreement, disaster. Now, after the talk, at the break, many people, theorists, experimentalists came to me congratulating me. So for a second, I thought I would be coming in December to Stockholm again, of course with Gerhard. This didn't happen, otherwise you will hear about it. And in fact, the situation improved, at least as concerned the deviation and maybe presence of some physics. These are the new values with one misprint here. This should be 10, also of another decay, which is even more suppressed. So there is some kind of possibly anomaly, but the main point is that if you have seen this, there is simply no idea to find out what it is. You will have 100 theories claiming something else. So you really, you have to look at all these decays. I will not go through them because we have maybe not so much time, but also leptons and others. And you have to really make many precision observables, have precise theory, and as I will show you in a moment, what is very important before you start making some very complicated Monte Carlo, whatever PIs and so on, what the young generation is doing, which is fine, but I think we should do it first, understand what is going on, correlation between many observables. So the idea is, first of all, you have to work 24 hours over the clock. There are all these transitions here, like chemical, this transition which we have, which I will now probe. And you go and study many models. So you study many models, and what you do is for each of this model, this is what I will do now. You take one, some Z's, some leptocores, I will mention them later. You simply always studied in my group. You simply, for each theory, you look what happens for all these decays. And here comes the basic idea. With my granddaughter here, Jennifer, the idea is simply to see in a given theory whether the probability of this decay, transition to happen is increased. Maybe there is no change, maybe there is decrease relative to standard model. So you go, you work 24 hours, and this is one theory, there is a second theory, there is a third theory, fourth theory, fifth theory, and you can see there is some DNA, some pattern, and we have eventually experiment. You compare on one transparency, and if you compare very precisely, everything is ruled out. And this means you still there, down there in India, you can construct your own theory, and maybe it will work. Of course, we are not at the situation to draw such diagrams, but there is some weak point in the first step, and I will tell you now. Second step, the point is that any theory, unless this is completely, like gravity or something like this, has three parameters. So if you say, okay, it goes up, there is some deviations, you will fit your parameter, one parameter, second parameter, so it works. But eventually, there are not 100 parameters like in supersymmetry. What will happen, that there will be some kind of correlation. You say, I have to increase some probability for one decay, but then there will be suppression. And this brings me to a second idea developed with Jennifer, this correlation. So I have correlation, is given here, anti-correlation by this arrow. And I will show you just 4 examples, just to give idea that indeed, if we measure all this, we will be able to say something. This is so-called minimal flavor violation, very modest extension from the standard model based on some flavor symmetry. This is unitary symmetry 3. Whatever it is, it's not so important. But there are some correlations in this. So if, for instance, I have to enhance this up to 2 muons, in fact, what we have seen, if there is this anomaly, I have to suppress it. I went too fast. I go back. And then I will also have to suppress here. There's one thing maybe interesting, and in fact, this part was done with Monica Blanke, is that in this world, this observables, which the mixing and CP violation of particle physics is a message, can only be enhanced. So if the data are below the standard model prediction, this symmetry is out. And there are other correlations, but now, if it doesn't work, you can reduce the symmetry, this flavor symmetry here in the corner, and you go to this one. So this is a smaller symmetry. And as you can see, already some correlation disappeared. And if you now go here and here, you really see the difference. That this is the first thing I would look if I have this decays. Does it work? Doesn't work. And now 2 other examples. This is Z prime with Z. I can do similar things at some loop level. And I have a Z prime, a new heavy gauge boson, much heavier than 20 TeV, but it interacts with our quarks only with the left-handed count. And then, again, I find some correlations. Okay, long to 2 muons, enhanced, this must be enhanced, and so on and so on. But it could be that it's only right-handed. As you can see, it's completely different. There's some correlation, anti-correlation. So this is basically the idea, and I think I have to move to the next movement, and this is anomalies in flavor physics. Now let us first go to 1983. In 1983, W and Z have been discovered, and one of the guests at Max Planck Institute was a very well-known physicist, Victor Weisskopf. And everybody was excited because standard model particles W and Z were found. And he stated, if experiment agrees with theory, there is no progress. And some people said the guy got old and he's taking some nonsense. But of course he was right. And this is the situation if you have the theory and you have experiment, and then experiment confirms there is a W and Z. But the opposite situations, that you have already experiment, but the theory is so complicated that you have wait. And I'm approaching 75 years, and this is what he was. So this is my statement for me. If the theory agrees with experiment, there is no progress. Obviously, these days, after what I told you, this great gentleman, me here, are of course right. And what is really fantastic, we have anomalies. We have anomalies, and there are many. In particular, in the last decade, many have been discovered. Some ratios, which I will still tell you a few things about, so-called B-physics anomalies. We have seen one, maybe. There is one which is controversial. I'll tell you maybe why, and a few others. So there are anomalies. But the most popular anomalies were indeed in B-physics. And there are many papers, I don't know, maybe 800, maybe 1,000 and so on this. And this effort could be compared to the climbing of Mount Everest. This is Hillary step. And you should see one very peculiar thing. These people wear masks, but there is no distancing whatsoever. So this is B-physics. Now, I didn't contribute very much. You will not find me there. And I put money on K-meson physics. And K-meson physics is very different. This is like hiking in Norwegian mountains. You are alone. You don't need any mask. You can even be separated from your wife, who is taking the photo. And most importantly, when you are alone, you can think. You don't have to watch some paper will come tomorrow. I have to publish. I make mistakes. And the next day I'm Prof. And so on and so on. Nonsense. And at some stage, you will get some results. So here is, first of all, my first collaborator, my best collaborator, he always ahead of me. And now let me go back to physics anomalies. So these are the ratios and what we have in the standard model, and maybe let's with 2 because it's easier. This ratio in the standard model should be 1 because the interaction of muons and electrons are universal in the standard model, but it's a bit smaller. In this case, it's even worse. There is the ratio. Otherwise, it would be unity. Here, it cannot be unity because there is some kinematical effect because this tau lepton is relatively heavy, so there is a phase space suppression. And therefore, you get this result. But here you can see there is some enhancement. And there are other things. So definitely, there are some departures which still have to be improved. And apparently, in a few weeks, we will have still some messages from one of the Morion conferences. So we will see whether this will be confirmed or not. And this is one picture of this ratio of R d star. This is going back the decay giving here for D R d star. 2, and there you have anomalies, and you see there are several experiments. This is the average, and here is a standard model, rather precisely now. And definitely there is something, and if you do some analysis, proper Monte Carlo and so on, Bayesian, whatever you do, apparently you get something like 5 sigma. Now, the question is, what is behind? Now, one thing which we know already, that this is not supersymmetry. Supersymmetry cannot explain it or have difficulties to explain these anomalies, and the 2 really leading candidates are either the Z prime boson, a heavy one, maybe only 2, 3 TeV, maybe it could be discovered at Collider the next years, and a very interesting object, and this is a leptoquark. And this is lepton quark, this is spin 0, 1, which connects directly lepton and quark. Such objects are known from grand unification theories where you unify leptons and quarks. But this lepton quarks, in order to explain the anomalies I was talking about, they have to be maybe at most 5 TeV. So maybe we can see them. This would be a really fantastic thing to find this object. I still believe that at some stage we will also see quarks, but the vector-like, where left and right hand interact in the same way. And the other anomalies. One anomaly which is already for 20 years with us, and we will get a message from Fermilab. This is the result from Brookhaven, which shows some anomaly, apparently by the master of this calculation, Jägerlehne, for sigma. And there is also, I claim, but not everybody agrees with me, I will say a few words about it, anomaly in CP violation, which I talk, in the case k going to pi, in so-called K0, K0 bar mixing, epsilon, it's roughly okay. And this is an example that we have already experiment, I will tell you. But the theory is so complicated that we have no still result. And this is roughly what, as a first attempt, I can use this language, which I was showing you, just showing what experiment is telling me on these quantities on the left and right. And this is plus or minus required for new physics to really fit the experiment. And lepton quarks cannot do it completely. Are doing pretty well. Z prime cannot either in this case. And the thing, what is really very good is that both can do it, and maybe you can have other particles like vector, like quarks and so on. But we really need more data to identify it. And now, since my wife is not taking pictures of me now, and she doesn't listen to this talk, she doesn't want to know anything about it, let me tell you about my love starting in 83. These are last minutes. And this is related to one approach which I developed. And I have to tell you, not many people approve it. In my laudatio for Max Planck medal, it was not mentioned. Strong interactions are very complicated, as you know. But there is a symmetry SU3. N is 3, this is 3 colors, and these ideas, and there are similar ideas in solid state physics with ON, orthogonal symmetries, really allow for large N to show, and this was dominantly Witten, that QCD becomes a theory of weakly interacting mesons. And the thing is that then we notice that if we really go to large N, it's a free theory. In Munich with 2 gentlemen, which I will show you in a moment. And this means that some objects, which are very complicated, and there are some very strongly interacting mesons, like, for instance, K going to pi, 3 bound states, can be much simpler calculated. But you have to go, of course, beyond it. And this is a called dual QCD approach developed by Bardeen, Gerard, was already mentioned, as one of my best collaborators, and myself in 83, 2016. And I can tell you, and some people agree with that, this is a very successful ONG approach, well ahead of what Lattice has done. But the main reason I'm showing this transparency, that after so many years, my collaborators do not look as well as previously, and I, you have to admit, improved significantly. Although I'm getting worse again. Now, epsilon prime. This ratio was measured with some precision. It took also 10, 20 years to do it by this collaboration, one at CERN, one at Fermilab. And there are 3 groups, which I cannot go into details, which try to predict in a standard model. This is very difficult because you have to calculate some hadronic matrix elements. And this is the statement of Tony Peake, is his group. And that this agrees very well with experiment. I claim it is not from the inside of dual QCD, and I get support from Gerard, of course. If you are interested, read my arguments. This is the first preprint in high energy physics which appeared in this year. And Lattice last year produced the data which were, however, incomplete because certain things like isospin breaking effects they didn't include. They will include in the next 5 years. And we included them, and from their data, which were around 20, the central values of complete different value, one gets agreement between chiral perturbation theory and lattice. But the point is that this is if I discuss in this paper here, this is an accident agreement. I believe lattice will, as I discussed, they will one day reach, and I think they will agree with me. This is global symmetries. They cannot do it. And you see, I'm stressing this. I'm extremely delighted. I disagree with these two groups because they will be confirmed one day. Like Van Leeuwenhoek, I will get the credit, not the other guys. So I'm sure they will be claiming that they get credit. This is life. So these are the finding anomalies. I have to go a bit faster. Now, there is here another puzzle for many years, already in 1955, where without QCD, one had square root of 2. People tried to, through asymptotic freedom, explain it, Altarini-Majani, Gajaren-Lee. They failed. And we succeeded with our approach, which is finding big effects below 1 GeV scale. It's non-perturbative. And recently also lattice also got it. Whether there is some new dynamics still, I don't know. This is the case I'm waiting already many years. And they are very clean as opposed to what I discussed just previously. And they are very well known. And we know already some results. So here are the most recent results, which you can compare. The first one is still a big error, but it's roughly consistent with experiment. The second one, there is the bound and there are some events, amazing result. Maybe there is something, I'm not so sure, but I don't know, I didn't study like that. But what I want to point here, that with these correlations, there are correlation between these decays. I discussed correlation, and there is one with big insight from Monica some time ago, who demonstrated that if, in addition to this decays, in some new physics scenario with only left-handed couplings, then the only place where you can find any result on this plot are these two lines. Either you have nothing in K long, or you have to grow roughly parallel to this bound. And if you have left and right, of course, you have more parameters, and then you can be somewhere else. And there is minimal flavor violation, also not in a very good shape, will be at some stage. But we will see. We have to wait. I'm answering the question, and then there will be closing remarks. We have made a big study of this decays with Z prime and also with some heavy scalars. And here is the list that indeed, with this decays, provided experiments will be precise, provided this theory will be precise. In this case, the theory I claim is already precise. We will be able to reach this very high scale. And the message here is also that K physics has a bit easier time. So I have, I think, only 1 minute or 2 minutes. Force movement, finale. Vivace, the message I hope from my talk is clear. This rare decays will play a crucial role in identifying new physics, hopefully present on our route. I mean, it could be that, we have to go even further. And here, for instance, lepton flavor violation would be important. Unfortunately, we didn't see any lepton flavor violation experiment, also no electric dipole moments have been measured. And therefore, we don't know. And so there are indeed very exciting time ahead of us. And these are the things which we really have to attack, and both theory and experiment, lattice, improved. There is really still a lot to do, new ideas how to improve on this DNA chart. And fortunately, we have some science, not only dark matter, not only neutrino masses. We have some science that there is something there. So we will have this expedition probably even beyond 2030 from Zeptouniverse to Zeptouniverse, which I hope some of you will join, some will only watch. But we should realize that we should be patient, because it will take some time before we reach Zeptouniverse. And if you invite me again, in 2030, the only thing I can predict that you and me will be a bit older. And my son tells me that this is my son Alan, tells me that I'm optimistic, but we will see. We can compare in 2030 if I'm alive. Otherwise, we cannot compare. So this route is really very complicated. And as in an expedition, you need some guide which would tell you how efficiently to reach Zeptouniverse in this case. And the last 7 years, I worked on a guide like this and finally completed in July 2020. And it has many references, many pages, and I hope it will help some people one day to reach Zeptouniverse. Thank you very much.
Thank you, Andrzej, for such a nice talk.
Yes, I'm here. I'm watching. I don't know. I see you probably somewhere. Yes. Maybe there are some questions. Thank you.
Yeah, so it's a time for some questions.
Yes, there are some questions. I don't see them. Maybe nobody has a question. No questions. Okay.
Rajiv, you can go ahead if you have some question.
Yeah, sir. I have a question, a particular question regarding this B2 K star mu mu decays.
Which one? Bisapes 2 to mu ones?
No, B2 K star. B2 K star mu mu or K star anomaly.
Oh, BK star anomaly.
Okay, so in that case, the fact related to factorizations, there will be some effects from the spectator quarks, right?
Yes, sorry, I don't know, maybe this is the problem with my loudspeaker. I cannot hear you. I cannot.
Maybe you can mute your microphone probably.
Yeah, okay, but say once more, I repeat, are you talking, maybe I go back, are you talking about BK star anomalies?
Yes, in that anomaly, the effect of spectator quarks.
Yes.
So how does they affect the lepton flavor universality? There will be, of course, there will be effect on the say the different.
You are talking about this one, BK star. Okay, good.
Okay,
I mean,
so
there will be. I must admit, I didn't study in detail. There were people who studied this anomalies, and there could be some spectator, but I would be surprised, because the spectator, I would claim, the spectator, if this is how the spectator is universal and doesn't enter the vertex, if you have some Z prime. So I'm not sure this is the issue. More, I believe, if you see, you take a ratio, I could imagine, maybe I'm wrong, but I could imagine that the Dutch effects are cancelled in the ratio.
Okay.
And on the other hand, if you maybe, but okay, there is some asymmetries, maybe there you would see more, but I don't think it will be so important. But maybe there are some experts on RK star in the audience which can answer this question. I didn't touch this. Partly, I must admit, I expect that they will go away, but I hope they will stay.
Thank you, sir.
Yeah.
Anyone else have any question? You can directly ask if you have a question. You don't need to raise your hand. Okay, Pankaj, maybe you can end the session with the end.
Okay, if there is no further question, then we are once again thanks Andrzej for such a nice talk, and we hope that sometimes he would take a time and visit us when the pandemic situation get over. We'd be happy to host him here. And with this, I just hand over to Sumitro to say a few words.
It's okay. Thanks, Andrzej, to agree to give a talk, and it's okay. I hope we'll get you later on also at some point. Okay, so like maybe
we will see. We will see. Okay, thanks a lot for inviting me.
Yeah.
Thank you.
Okay. Yeah, great.
Okay, bye-bye.
Yeah, bye-bye.
Okay, thank you all. Bye.
Thank you. Bye-bye.
Bye-bye, Professor Buras.
Yep, bye-bye.
Thank you.